So page 148 to 150. This is where we're going to introduce type 1 and type 2 errors, and we're going to go through definitions, and it's going to be a whole lot of material, and you may need to pause and go back, etc., to go over some stuff. So when we collect data, we are collecting a sample, and as a consequence, there's sample variation. That sampling variation or sample error leads to error in our decision making. In other words, best statisticians aren't perfect. Matter of fact, no one in life is perfect, and we actually like to quantify how often we make errors or believe that we make errors in statistics. And so when we perform a hypothesis test, we can make mistakes in two ways. And really, I shouldn't say mistakes, I should say errors in two ways. One, the null hypothesis is true, but we mistakenly reject it. That's a type 1 or alpha. Or the null hypothesis is false, but we fail to reject it, and that's a type 2 or error or beta. Now, quite frankly, the language of rejecting nulls, the language of type 1 and type 2 is a little bit confusing. So I'm going to give you some ways to memorize this, and maybe so write this down. I think this will help you out a little bit. So we have type 1, and we have type 2. I know that's really creative. And I want you to think about the alphabet. The very first letter is A, which is also the first letter in alpha. And alpha is the first letter in the Greek alphabet. And the reason we say that is alpha measures the probability of a type 1 error. Type 2 is measured by B, or more correctly, beta. And that's the probability of committing a type 2 error. Now, it also gets difficult on what phrase goes with which. I don't have a good way to memorize this one yet, but I do have a really good way to memorize this one. This is only occurs if you fail to reject. This only occurs if you fail to reject. So think about this. First off, just because you fail to reject doesn't mean it's wrong. You might need to do that. That might be the right decision. But if you fail to reject, the only type of error you can commit is a type 2. You can't commit a type 1. So if I fail to reject, the only type of error that might have been committed is a type 2. All right. With a type 1, the only type of error I can commit is a rejection. All right. So here I rejected. And now just because you reject the null doesn't mean you committed a type 1. You might have done the right thing. But if I do reject, I can't commit a type 2. The only type I can commit is a type 1. So type 1 is related to A for alpha, first letter. And if you reject, you might have committed one. Type 2, B for beta, the second letter of the alphabet. And that only could have happened if you failed to reject. Once again, if you fail to reject, the only type is a type 2. If you reject, the only type of error you can commit is a type 1. Hopefully that'll help you in memorizing this. So here's an illustration that, quite frankly, they show in every single textbook. It's the one I grew up with. It helps some people. It doesn't necessarily help everybody, but it's the decision box. It's always presented. So this says the truth, and I'm going to just call it reality, all right? This is the real world. This is our decision based on statistics, based on the data we collected. So let's assume or believe or given that the null is really true. So given that the null is really true, we could have rejected the null. Well, if I reject the truth, that's a mistake. That's an error. And the only type of error I could have committed is a type 1. So if I reject the truth, if I reject the null, I committed a type 1. However, I might have rejected the null when it was false. if I reject the null when it's false, I made a correct decision. So rejecting the null when it's false is a correct decision, all right, and no error was committed. This is doing the right thing. This is correct. On the other hand, the null may have been true, and I kept the null. I retained it. I failed to reject. So instead of retain, we probably should have written failed to reject. Well, if I failed to reject a true null, that's good. I did not reject the truth. That's a correct decision. Over here, if I fail to reject a false null, that's a mistake. All right. So if we reject, the only type of error that we can commit is a type 1. If we fail to reject, the only type of error that we can commit is a type 2. As I said earlier, alpha is a probability of committing a type 1 error. Once again, this is a conditional probability, which is given that the null is in fact true, what's this is the probability that we will reject it. All right. We've already talked about the reason we don't want a very small alpha is because if we have a super small alpha, then it becomes very difficult to reject a false null. So here's one thing I want to point out to you. There's a relationship between alpha. As alpha goes up, beta goes down. As alpha goes up, beta goes down, and vice versa. So if I choose a small alpha, then my probability, if I choose a small, so if I have a large alpha, probability of a type 1 error is pretty big, and the probability of type 2 error is small. On the other hand, if I decrease alpha, the probability of a type 2 error goes up. So there's a balancing act there, and you're going to have to determine which way you want to go. So alpha is a conditional probability. Beta is also a conditional probability. And it's the probability of failing to reject a null given that the null is in fact false. All right. Now, one thing is when it comes to calculations, et cetera, alpha is easy because generally speaking, we pick it ourselves. We predetermine it. Well, students always want to go, hey, they see this is a relationship here, and they want to say A plus B equals 1. Alpha plus beta equals 1. That is false. Alpha plus beta does not equal 1. All right? And you probably should write that down. Alpha plus beta does not equal 1, and never forget it. So if I give you alpha, you don't have a way to figure out beta. If I give you beta, you don't have a way to figure out alpha. All right? So alpha plus beta does not equal 1. We can reduce type 2 error by increasing sample size. This is a pretty important concept. Sample variation gets better when we increase sample size, so our sampling error gets better. So increasing sample size is a good way to reduce type 2 error. Type 1 error, how do we reduce it? We choose a smaller alpha, and we arbitrarily choose that. But typically we choose something around 5%. Power. Power is not an error. So write that. Not an error. Not only that, it's a good thing. The probability of correct is a good thing, rejecting a false null. All right. Power is also, of course, not surprisingly, a conditional probability. The probability of rejecting the null given that it's false. All right. Now, power does have a formula. Power follows the formula. Power equals 1 minus beta. So if I give you the probability of a type 2 error, you can figure out power. If I tell you the power, you can figure out the probability of a type 2 error. All right. Obviously, as beta goes up, power gets smaller and vice versa. All right. Also, if we increase our alpha level, power goes up. And I'll go over those relationships in a further video when we're talking about the recipe cards. So I talked earlier and said that there is a relationship between alpha and beta. And you can read this top part of the sheet because I think it's basically redefining type 1 error and type 2 error, which I think I've already gone over in pretty good detail. But I want you to see this diagram of the way things work. So we have two normal curves with exactly the same the same shape. Now, I want you to see the relationship between alpha and beta. First off, if I look at alpha here and beta there, I can certainly see that alpha plus beta does not equal 1, right? I don't want you to forget that. But if I push on this bar in this direction, if I push it this way, alpha gets smaller. And so as alpha goes down, what happens to beta? Beta increases, all right? And also as I push it that way, as alpha goes down, beta increases and power also decreases. And you're like, well, why does alpha and power move together? Well, alpha is how we determine whether or not we're going to reject. So the larger the alpha, the easier it is to reject. So the larger the alpha, it's easier to reject, which means we have an easier opportunity of rejecting correctly, not just rejecting when it's incorrect. If, on the other hand, I push the bar this way, so if I push the bar back to the left, now alpha is going up and beta is going down and power goes up. So you can see that alpha and power move together and beta moves in the opposite direction. I'm going to just tell you this little part right down here, super important to learn, all right? As alpha increases, beta decreases, and power increases. Well, that's what we just showed. And the result consequences, we're more likely to reject the null hypothesis. Alpha increases, it's easier to reject. But what that means, alpha measures a type 1, so we're more likely to commit a type 1 error. Beta decreases, which means, oh, that's a good thing, we're less likely to commit a type 2 error, all right? So essentially this is neutral because being more likely to reject may be a good thing or a bad thing. Or more likely to commit a type 1 error, well, that's bad. Less likely to commit a type 2, well, that's good. All right, so you can see that it's like, well, gosh, I got to trade off between good and bad. As alpha decreases, we're less likely to reject the null hypothesis. Well, that's essentially neutral because you don't know if it was a good one or a bad one. But we're less likely to commit a type 1. Well, that's a good thing. But we're more likely to commit a type 2, and that's a bad thing. So obviously, we have trade-offs there when we change our alpha levels. Okay, next thing, putting this diagram actually into a real scenario or into a scenario that makes sense. So a teacher claims that the test average is 70%. So I claim that my students had a 70 average, but you've heard some scores, so you believe that the true figure is lower. And you plan to gather a simple random sample because you're a good statistician and will reject the claim if the sample test average is 65 or less. In other words, you're saying, you know, I don't really believe Mr. Spencer's telling the truth about that 70, but I'm going to give him some grace because I know there's some randomness in data. So if it's a 65, 66, 67, 68, 69, if the average of my samples anywhere in there or higher, I'm going to believe him. I'm just not, I'm not going to believe him, but I'm not going to reject his claim. However, if my sample, if the sample you take happens to be less than 65, you're going to say, you know what? I don't believe Mr. Spencer. That test average was definitely lower than 70. So if we were running the hypothesis test, we'd say, well, Mr. Spencer's claim is 70, so that's what we're going to write. And the alternative is what you think you're trying to show is that it's actually less than 70. So why are you setting mine as a null? And it's because I'm currently the innocent man, so my claim of 70 stands until you prove otherwise. Basically, please note the 70 matches, 65 matches, 60 and 55 and 50. So essentially, this is just an extension of that number line. Alpha is the rejection zone, all right? So if you get a score less than 65 for your sample, you're going to reject. Now, this is my claim. I claim that the test average was a 70. And so the grades, we'll assume, were normally distributed about 70, some above, some below. And it's possible that you, if my claim were true and if it looked like this, you're not going to reject in this area, all right? And that's if my claim is true, that's no problem. But if my claim, but it's possible in this little area that you would reject, and that would be a mistake if this were true. If this were true. However, in this particular case, the reality is I was lying. The test average was a 60. Okay, well, if the test average is a 60, then you should be rejecting me. All right, because this is actually turns out that it's not this, it's actually here. So this is the failure to reject, because you're going to fail to reject if you get a 60, if your sample is 65 or higher. Anything below 65, you're going to correctly reject, because we said that was false, and this is actually ended up being the reality. So anything below 65, you're going to reject, and that's our power. So the upper graph shows the null hypothesis model with the claim that mu is 70, and the plan to reject the null if mu is 65. When will we fail to reject the null hypothesis that mu is 70? Well, failing to reject is measured by beta, which is a type 2, and failing to reject would be this area right here. And we fail to reject the teacher's claim for any sample with an average greater than 65. This would result in a type 2 error because we know that the actual average is 60. All right, only because I told you that, but that's what we know. When will we rightly conclude that the null hypothesis is incorrect or that the null hypothesis is wrong? Well, we'll rightly conclude that if you get a sample of 65 or lower. All right, so we'll correctly reject the null hypothesis for any sample with an average less than 65. The probability that we would correctly reject the null is known as power. All right, given that the null is false, the probability we'll correctly reject it is known as power. Power gives the probability of avoiding a type 1 error because power equals 1 minus beta. Power has a different value for different possible values of the population parameter. What that means is, if instead of the 60, if the true average was 55, it'd be more likely to reject. If the true average was 50, it'd be even more likely to reject. If the true average was 40, you'd even be more likely to reject, because this curve would shift this way, and as this curve moves this way, beta would get a whole lot smaller because it would shift with it. Also, if the true average was 80, you'd be less likely to reject. All right, so we have something to say on to that. So choosing a different value for different possible correct values of the population parameter changes power. We can also say, as we increase the distance between the null and the true value, the smaller the risk of type 1. So as this curve as this curve moves this way, which means our true population mean here became 40 or whatever, our type 2 error decreased substantially. That's what's meant by that. So power increases as the true mean moves away from the hypothesized mean. So I think we should write that down. Power goes up as the true mean moves away from HO. All right. Now there is one limitation on that. It has to move in the direction of the alternative. So power would increase as we moved our move to the left. As we move to the left, power increases, and now because it's a less than. If it had been a greater than, power would increase as we move to the right. Okay, so power increases as the true mean moves away from the null hypothesis. All right, this concludes this video, the introduction to it. We will do a hypothesized scenario in the next one and give some more ideas on understanding type 1 and type 2 errors.